Hello, my name is Erik Idsti and I'm going to tell you about the commercialization effort from Carnegie Mellon University about making wafers for solar cells. So at present time, the state of art, it takes polysilicon, turns into a monocrystalline boule via something called the Czochralski process. These are expensive, $20,000 to $40,000 a pop, and possibly even more. They go through a step of diamond wire cutting, where they get the product. The industry standard is moving towards an M10 monocrystalline wafer with dimensions as you see here, and that goes into further production then. So in this process, due to the sawing and the batch processing, this is both labor intensive and also wasteful in terms of material. So what we want to do is to combine these two steps into a single continuous process, and we do this using something called horizontal ribbon growth. So we take the same raw material, polysilicon, feed it into a furnace where it melts. It flows into a stabilization part and then into the production part where we cool from above. So silicon is much like ice on water. When it's cooled, it will form a thin sheet that can be removed continuously while it freezes from behind. And then we get the flat ribbon that can be cut into wafers. We can go fairly wide with these. So our objective here is to produce an industry standard wafer as part of a continuous ribbon. Our cost analysis, as we'll see, come in about 30 cents per wafer versus 45 cents a wafer in Chinese production right now. So in the Go part of the contest, what we'd like to do is to demonstrate capability to produce an M10 commercial wafer. Essentially, what we need to look at are the thickness control, crystallinity and chemistry, and also verify the solar efficiency, and that we can do this at relatively high speed. So the pilot plant you see here represents about $2 million capital investment. The cost picture looks as follows. We essentially take the Chinese manufacturing cost, as you see on the left. We get rid of the sawing, we reduce the material requirement, and also reduce the direct labor cost, although we're producing in the United States. We did interviews with the largest silicon manufacturer, polysilicon, as well as solar cell manufacturers, and the take-home message, we learned a lot from these interviews, but the main take-home message was that they do want to see a commercial grade wafer before they want to commit to partnerships. Here's the team. We got a very varied and capable team with lots of experiences from different backgrounds and industries on the technology business side, and we also made good use of the American-made network. So towards industrialization, we're through the ready phase. We're sort of a little over halfway through set. We had the setback because of COVID, the lab closures. They're set to open again next week. So then we can move on to TRL by the end of the year. In the go phase, we want to solve the chemistry problems and produce an M10 demonstration wafer that will then lead to partnering and commercialization. So I think the main message here is that this process makes it viable to bring wafer manufacturing back to the US, but we do need to demonstrate the capability of making the wafer first. So thank you very much for your attention.